In this video, we'll be taking a look at the standard hydrogen electrode and standard electrode potentials. First, let's go ahead and recall what occurs in a voltaic cell. A voltaic cell consists of two metals of different activities. The more active metal loses its electrons more easily. The more active metal will transfer its electrons undergoing oxidation to the less active metal ion, which is reduced. In this animation here, you can see that zinc is the more active metal as it transfers its electrons to the copper ion and solid copper atoms are formed. The electrons are transferred from the zinc atom to the copper ions through the wire, and a voltage is produced and measured. From the spontaneous flow of electrons, voltage is produced. The voltage depends on the species used in the cell, their concentrations, and the temperature and pressure. Voltage is a measure of the cell potential, the potential for the anode to become oxidized and the cathode to become reduced. A larger cell potential means a higher voltage, and the more favorable the oxidation and reduction reaction taking place in the voltaic cell. The cell potential at standard conditions, which are solution concentrations of 1 mole per decimeter cubed at 298 Kelvin and 100 kilopascals for gases, is called the standard cell potential. The symbol next to the E cell here simply means that we're at standard conditions. The objective is to calculate the standard cell potential when a voltaic cell is constructed. So, can you calculate the voltage produced based on the metals used in the voltaic cell? The voltage produced, so the standard cell potential, is affected by both the species being reduced and the species being oxidized. In order to predict the standard cell potential for a voltaic cell, we have to develop a reference electrode. This reference electrode, or standard electrode, is a standard hydrogen electrode, abbreviated SHE. Here, we have hydrogen gas bubbled around a platinum electrode. The solution is a 1 molar solution of hydrochloric acid, so there's a high concentration of the hydrogen ion. The pressure is 100 kilopascals and the temperature is 298 Kelvin. Let's take a look and see what happens in the standard hydrogen electrode. In the standard hydrogen electrode, hydrogen gas is bubbled around a platinum electrode, coming in here from the tube on the left. The electrode is provided so that the reaction has a surface area on which to take place. The platinum itself is very unreactive. In the solution, you see that there's a high concentration of hydrogen ions. On the electrode, hydrogen gas can either be oxidized to form hydrogen ions, or hydrogen ions can be reduced to form hydrogen gas. Here, in this animation, you see that the hydrogen ions are reduced to form H2 gas. If the reverse process takes place, hydrogen is oxidized. Again, depending on the species that the standard hydrogen electrode is paired with, hydrogen might either be oxidized or reduced. Because oxidation and reduction for hydrogen are both possible, we can use a two-headed arrow to show the reaction. The reaction shown in red is the one given in the data booklet. The reaction is assigned a standard electrode potential of 0 volts, and it serves as a reference. As you remember, two half cells complete a voltaic cell. When one of the half cells is the standard hydrogen electrode, the cell potential is called the standard electrode potential and is the value assigned to the other half cell. Let's take a look at an example. Here on the left, we see that we have a zinc half cell, and on the right, we have the standard hydrogen electrode. We see that the electrons are moving from the zinc electrode to the standard hydrogen electrode, so zinc is being oxidized. Because the standard hydrogen electrode is assigned a potential of 0 volts, the oxidation of zinc is assigned the standard electrode potential of 0.76 volts. Here we have the list of standard electrode potentials as given in the data booklet. These standard electrode potentials are the voltage readings when these half cells are combined with the standard hydrogen electrode. Let's take a look at the reaction we just had, solid zinc forming the zinc 2+ ion. The cell potential previously was given as positive 0.76 volts, but here we see the standard electrode potential is a negative 0.76 volts. Why the difference in positive and negative? Standard electrode potentials are always written as reduction reactions. This is done in order to simplify the process. Remember, in the standard hydrogen electrode, hydrogen can either be oxidized or reduced. A negative sign for the standard electrode potential indicates that reduction is not favorable. Rather, the species would prefer to be oxidized. So here, if we look back at the reduction reaction for zinc, the standard electrode potential is negative because zinc would rather be oxidized, as we diagrammed earlier. In order for the metal atoms to be oxidized to form cations, the reactions must be reversed. When the reactions are reversed, the sign of the standard electrode potential changes. That's where we get the positive 0.76 from that we saw earlier. If we go ahead and look at the second part of our table, we see all the way at the bottom we're dealing with our halogens. We see now that the standard electrode potentials are positive, so the process is favorable. We know that this is correct as the halogens will gain electrons, become reduced, and form the anions. And so, the standard electrode potential is the voltage of the reduction half equation relative to the standard hydrogen electrode.